Hello everyone. Welcome to this session on hydroprocessing of digital elevation model and catchment delineation using QGIS, part 1. In our earlier sessions, we learned how to work with raster and vector data, how to perform basic spatial analysis, and change symbology for visualization of layers. We have also worked with digital elevation model. We are now going a step ahead into hydrological analysis using digital elevation models. We will be delineating drainage network and catchment boundaries in this session using SAGA tools. As you know, as you are aware, catchment delineation is of great interest to all hydrologists. In this session, we will be using SAGA tools. SAGA stands for System for Automated Geoscientific Analysis, which can be integrated. It is like a third-party package which can be integrated with QGIS. In the subsequent session, we will be using GRASH tool so as to provide an alternative. While SAGA tools are faster, there has been some issue with support, official support. Both SAGA and GRASH used to come along with QGIS installation, standalone installation. But of late, as I said, there is some issue with official support. So we want to have an alternative using GRASH tools, which are more robust, even though they are a bit slow. So let us start with today's session. Catchment delineation using any GIS application, it involves identifying and demarcating the boundaries of an area draining to a particular outlet point or pour point on the stream network located on a stream network. Now the DEM which is used as an input for catchment delineation, it may be not be accurate, it may be having many errors. At the time of data acquisition, there may be the DEM may have got artifacts. There may be sinks in the DEM which will not allow for which will affect the accuracy of hydrological analysis. So you need to make your DEM hydrologically conditioned. Hydrosheds.org portal, which we have seen in the session on open access datasets, it provides an hydrologically conditioned DEM. Uh, the SRTM DEM was used as an input to generate that. There are several algorithms for filling the sinks. You will come across such algorithms in the tools in the processing toolbox of QGIS under SAGA tools and the GRASH tools. Once you generate a depressionless DEM, it is used as an input for generation of flow direction. Now, flow direction, again, there are many options which are available. From a pixel, water can flow into the surrounding 8 pixels depending upon the steepness of the slope. If it is D8 algorithm, the water will flow in any one particular of the 8 directions in the steepest flow in the direction of the steepest descent of the flow in the direction of the steepest slope. Similarly, there are other algorithms where water will flow in multiple directions. There is a D infinity. There is multiple flow direction algorithm, which may be useful for delineation or stream generation in particular settings. Now, once you have the flow direction, then you can generate the flow accumulation. It is nothing but the number of cells draining to a specific location, the number of cells contributing to the flow, including that particular cell. And once you have this flow accumulation raster, you can decide the threshold for generation of the stream network. Now, in the similar way, you can decide upon the threshold of the stream order for generation of the stream network. Um, if you don't do the thresholding, if you generate a very dense network of streams starting from the first order stream, it will not serve any purpose of delineation other than consuming your resources. So you can accordingly choose a threshold value, and then you generate the stream network, delineation of the stream network based on this threshold value from flow accumulation raster, and then you define a outlet point or the pour point on the generated stream network based upon your the idea locational context that you collect a pour point from the field, outlet point from a field. It could be a location of a dam, it could be a gas site, it could be a proposed site for for a dam, or it could be a confluence point of a tributary just before it is confluencing with the main river. So you can have the coordinates of that particular outlet point, but it should when you want to make use of the DEM, the input DEM and the channel network for generation of the catchment, for delineation of the catchment, this outlet point or the pour point has to be necessarily on the catchment that has been derived. The catchment, sorry, the stream network that has been derived. The stream network may not be accurate, but it has to be on the pour point has to be on the stream network. So for that purpose, we will see how we can capture the coordinates on the stream and choose the decide the pour point. Um, Even if you have the coordinates of the outlet point, you have to choose the coordinates, the nearby coordinates on the stream, which has been stream that has been generated, and then you delineate the catchment. So this is the general steps or procedure that is involved um, for catchment delineation. In this session, we will be downloading the SRTM 1 arc second 30-meter resolution DEM tiles from USGS Earth Explorer, and we will be delineating the catchment of Bhima Basin. Bhima River is a tributary of Krishna River. You can even use the Cotodem tiles from Bhuvan portal. The procedure will be the same. The source can be SRTM tiles or Cotodem tiles. You can even go for SRTM 90-meter resolution void field data from CGIAR CSI GeoPortal, where you have big tiles are there, 5 degree by 5 degree, and almost the entire Bhima basin will be covered by, I think, 2 tiles. It will be enough. The resolution of pixel is 90 meter, therefore your processing will be fast. The catchment boundary delineated will be slightly different from 90-meter resolution SRTM and 30-meter resolution SRTM, but at that level, at that scale, it will not make much difference. So let us quickly go to USGS Earth Explorer portal and let us download the tiles, DEM tiles. So you log in with your credentials. You in the such criteria, enter such criteria, you select geocoder, and the method you select it as address or place, and here under address slash place you type Bhima River and then click on show. Then it will show you the location, some location of Bhima River. You can click to see the in the map canvas. This is the Bhima River, which is this is somewhere in Karnataka, the boundary between two districts of Kalburgi and Vijaypura. Now let me check the river. The point of confluence of the river with the Krishna is in the downstream. near Telangana Karnataka border. You can see this is Krishna River, whereas this is Bhima River. So your outlet point will be somewhere here before, just before the confluence, and the upper catchment will be covering up to this point, the water divide of Western Ghats. Pune also comes under upper Bhima basin. So you zoom the map canvas extent so that it covers the entire Bhima basin, and then you can click on this use map. It will create a bounding box. You can change the coordinates by dragging them. So this is my area of interest. Now I will once you have decided the area of interest, you can, generally we go for larger area of interest covering the basin and also the adjoining area. You should never fall short of the basin boundaries, otherwise it will give you erroneous results. If you are having it for extended area, the same setup can be used for delineation of even the adjoining catchments also, like this west flowing rivers. Also for the same setup we can delineate. Anyway, you click on datasets. So in the second tab under datasets, you check for digital elevation. You choose the SRTM 1 arc second global, and then click on results tab. And here you will find about 20 tiles which are intersecting this area. So you can check the footprint of each of these tiles. So you can download these tiles by checking this option, and you can download the GeoTIFF format in a GeoTIFF format. I have already done this, and all the downloaded tiles I have kept it in day 4 folder, exercise data SRTM. I have downloaded about 19 tiles covering the entire Bhima basin. So once you complete the downloading of all the DEM tiles, you can launch QGIS and you can create a new project and save your project under day 4 solution. You give it the name Bhima Catchment Delineation. Now you can add all the 19 tiles, raster tiles, onto your layer panel. In case if your browser panel is not showing up, you can go to the view option and then check the under panels the browser panel. For ease of access, you can locate your folder containing your data. That is under downloads. We have it under day 4. You can right click on the folder and add it as a favorite, and then you will find the option the folder will be available under favorite, and under exercise data under SRTM. So you can select all these 19 tiles and drag them onto your layers panel. Alternately, you can add go to the option of add layer and add raster layer and select each of these tiles and add them to the layers panel. This is more easier. Now once it is done, you can cross this browser panel. So you have these 19 tiles. Each tile is represented in its default visualization by its default visualization parameters depending upon the range of the values of elevation. You can check the symbology of by clicking the layer properties. You see every tile is displayed rendered in single band gray between its minimum and maximum values. Therefore you see this blocky appearance. Now we will try to merge all the 19 tiles to create a single raster DEM layer for further usage. You can also check other metadata of these tiles. You have to know, you can check the CRS, which is WGS 84 EPSG 4326, that is the global coordinate system. You can see the pixel size, which is 0.00027777, which means it is about, if you multiply this with the 3600 seconds, it is about 1 arc second, that is 30-meter resolution. You can also check the no data value of each tile, which is minus 32767. So no data value, we have seen that it is considered wherever the pixel value is this much, it will not be considered for the analysis. Now why I require the no data value? Because if I don't give you the merged layer, now let us come to that. Um, the option for merging the layers will be under the raster, then miscellaneous and merge option. You can access the same tool from processing toolbox, and you search for merge in the processing toolbox. You will find it under GDAL, raster, miscellaneous and merge. It will give you the same dialog box. The processing framework is the heart of QGIS. You will find hundreds of tools which are there, the core tools of QGIS, as well as additional tools from GRASS, SAGA. Some of the important one are listed under the in the main menu. So here you can go to this option of select input layers and click on select all, and then under advanced parameters you can assign specified no data value, which will be the no data value specified no data value to the output, that is the merged tile that you are going to generate. You want to have the same no data value as in the individual tiles. So you can input minus 32767. If you don't give this value, what will happen is, because there is the extent is not full, this tile here in the merged tile, it will give you the value of 0. Now if you are giving a specified no data value, it will be treated as no data only. So then you can save the merged layer onto the file by giving the under solution, you can save it as DEM merged, and then save it, and then you can run this algorithm, which will be, once it is completed after merging the layer, it will display a message that the algorithm has finished running, and the layer will be added to the map canvas as well as the layers panel. So this is also, this process of merging is also known as mosaicing. In case if you are going for SRTM 90-meter resolution tiles from the CGIAR CSI portal, there will be only 2 tiles covering the entire Bhima basin. So I can drag the DEM merged onto the top. You can see all the blocky appearance has gone. Now I no longer require these 19 tiles in my layers panel. What I can do is I can delete them. Before that, you have installed one plugin in the last session, which is value tool. If you check this value tool again, you can simply check the values of the DEM merged as well as the any of those 19 tiles, you can see the values should be the same, 495 and 495. The number of rows and columns will be different because DEM merged is for extended area. So anyway, let me remove all these layers, 19 layers, and I will only keep a merged layer for further procedure. You can check the metadata of the merged layer. It will have the same pixel size. The CRS is EPSG 4326 WGS84, which is Global Coordinate System. Now, because we are going to delineate catchments and we want to calculate the area of the catchment, and because the elevation value is stored in meters in each pixel, it is more convenient for us to reproject this DEM um, into some UTM, like for this Bhima basin. Most of the basin is in UTM 43 north. So you can reproject this DEM into universal transverse marketer projected coordinate system that we will do. So you can also see the project CRS, which is the by default the initial layers which have been added, that has become the project CRS. Now for reprojection, we will go to the raster, and then under projections you will find this warp reproject. The same thing, if you go to toolbox and if you search for warp, you will find it under raster projections warp reproject. So you click the warp reproject. Here your input layer will be your DEM merged, which is in the coordinate CRS of EPSG 4326, that is Global Coordinate System. The source CRS, you can give the input. You will find it here, which is the project CRS. But still, in case if you are not finding anything, you can select this CRS option and then go to select the option of predefined CRS, and here you can search for the tile. You can search for the EPSG code and go back, and the target CRS, as it was shown in another session, you can look for your EPSG codes in this websites, either spatialreference.org or epsg.io. UTM 43 north, you can search. So you will see that UTM 43 north WGS 84, that is the datum, which is a universally accepted datum. These are other datums, Kalyanpur WGS 72. So the code is 32643, you can note down. And now we will reproject our layer. We can select this again, select CRS option, go to predefined CRS, and you search for 32643. Under projected coordinate system, you will find this UTM universal transverse marketer 43 zone 43N. You select this and go back. Now your source and target CRS are specified. Now the resampling method, you keep the nearest neighbor as it is to preserve the values. Also, it is better to use this nearest neighbor method. And the no data value for output bands, you can give -32767, the no data value. And the output file resolution, you can keep the same 30 meters, and then you can save your layer. If you don't save it, it will create a temporary layer and then you can save it. So the reprojected DEM, you can save it as save to file as DEM reprojected. Save and then run. Now once the algorithm is finished, it will display a message and your layer DEM reprojected will be added to the layer panel and the map canvas area. So it has been done. You can close this dialog and you can see DEM reprojected has been added to the layer panel. You can remove the DEM merged now. From now you can look at by scrolling the mouse onto the DEM reprojected, you can see the EPSG 32643. You can check the layer properties by going to information by double clicking the layer, or right click and go to properties. You will see the CRS as EPSG 32643. The units are in meters. You may notice that your project CRS is still EPSG 4326, that is global coordinate system, global coordinate reference system, even though you have reprojected your layer into UTM 43 North zone. Now to change the project CRS, you can click here in the right side bottom corner and then you can search in the this filter. You can search with the EPSG code 32643, that is UTM 43 North zone. Because we have used it recently, you will find it in the recently used CRS. Otherwise, you can for the first time, you can, if you want to search, you can you will find every predefined CRS under this section. You select it, the EPSG 32643 WGS 84 UTM zone 43 North, and then apply, then click on OK. Now you may have noticed that your layer DEM reprojected layer has slightly tilted after you changed the project CRS. Because now the visualization has also been changed to 32643. Now QGIS has on the fly projection that for visualization purpose. That means you whatever even if your layers are in different CRS, when you are adding the layers in the map canvas area, all of them will be shown in the project CRS, so that all the layers will overlay on top of each other, overlay nicely, even though their CRS is not actually being changed. So this is for visualization purpose only. Now you know that how the project CRS, if it is undefined, whatever be the first layer that you have added in that you added in the layers panel, it will pick up its CRS as the project CRS, because we added the first layers that we have added for this project are SRTM layers. SRTM layers, you can check their CRS is EPSG 4326, that is global coordinate system. Now why we want to change it to 32643? Because we want to have our coordinates, when you want to pick up the coordinates of your outlet, basin outlet, you need to have them in this CRS, that is UTM 43 North CRS, where the coordinates will be eastings and northings. You can see now the coordinates here in this bar, they are no longer degrees, they are in eastings and northings. That is the UTM coordinates. Now we will see processing framework of QGIS. We have been using many of the tools from processing toolbox. It is the heart of QGIS, where you will find all the tools, algorithms listed under different heads, like raster tools, raster analysis, network analysis, vector geometry, vector overlay, and all these tools are there. In addition, you also have GDAL and GRASS. Some of the GRASS tools are there. Earlier,
when one used to install QGIS, it used to standalone installer. It used to come along with SAGA, along with GRASS. Now SAGA, of late there has been issues with the support of official support of SAGA. Therefore, now if you see the new installation, you don't find SAGA tools. So these are like Saga and Grass, as we said, these are third-party packages with which can be integrated with QGIS. Many of the these are the basic tools and in QGIS. In addition, um, many of these tools are you will also find like raster calculator. All those things you will also find under Grass and Saga. And some of the tools in the Saga and Grass are much better, so you can use it for basin delineation purpose. The steps like filling of sinks, then generation of streams, etc. You don't have the tools in QGIS basic tools. You have to go for either Grass or Saga. But because Saga is not officially supported, now you have to do some installation of you can get those tools to a plugin. You have to install it and you have to make some changes in the settings that we will be doing now. So just in case if you are using old installation of QGIS and if you have the Saga tools here, you can check that many of the tools they may not be active, and you will also find one error message whenever you want to use Saga that it is not officially supported. So you need to uncheck the plugin of Saga GIS provider, and you have to install a new plugin. You can search for Saga, then you will find this new plugin, Processing Saga Next Gen Provider. So this, as it says, it is a processing provider for modern Saga releases, for latest releases. Previous releases, I think up to 7 point so and so version, there was support. But now this is the processing provider for Saga 9.2 and above. It requires, as it says, manual installation of Saga binaries. Now we will see how do we do that manual installation. Now it also in the description you will find since QGIS 3.30 Saga tools are no longer included in the standard installation. So in order to use the Saga tools in QGIS, you need to install this plugin first and then manually install Saga 9.2.0 or later versions. So to install this Saga 9.2.0, you can visit this URL sourceforge.net. We will see that. This plugin is tested on Saga 9.2 only. It may work for more recent releases of Saga. So after downloading Saga, you have to unzip that Saga 9.2 we will download, and we will see there are two alternatives. If you have installed your QGIS using network installer, then in that case you need not download this Saga 9.2, and we will see how to make changes in that case. Otherwise, in both ways you can go. That is, you can install Saga uh, 9.2 and you have to give the path to the folder. Alternately, you have to give the path to a folder which will be already there on your system. In both cases, as a first step, you need to compulsorily install this plugin, processing Saga Next Gen Provider. So all of you have to install this plugin. So you know how to install the plugin. Well, you ensure that you are connected to internet. It will hardly take few seconds time. So once it is installed, you can see that your plugin is installed, and make sure that you have a check it is the plugin is checked, the box is checked. Now you will also find under processing toolbox a new head has been added, SAGA Next Gen, under which you will find so many tools. You will find many of the tools which will be useful for basin delineation and terrain analysis. We will see them. So once it is done, now the next part is we have to manually install the SAGA binaries. As it says, it requires manual installation of SAGA binaries. So you need to first install this plugin and then manually install SAGA 9.2.0 or later. Where you will find it, you can find to install SAGA, you can visit this website. Then you click on SAGA 9, under which you will find all the SAGA 9.x versions. So go to SAGA 9.2.0, SAGA 9.2.0 folder, and inside it you will find, in the parent folder you will find these files. Now what you need to install is, you need to install SAGA binaries. So you will find this file, SAGA 9.2.0 x64.zip, that is for 64-bit system. A zip file will be there, is which is binaries for MS Windows 64-bit machines. Just unzip and run. So you have to install this, download this folder, and then give path to the folder. So to install this, you can check here. Yeah, this is the file that you need to install, SAGA 9.2.0 x this is a 64-bit system zip file. Click here, it will immediately start installation. Yeah, it is getting installed. Once it is done, you go to the folder where it is installed, SAGA 9.2.0 x64. You right click and extract all the files. You can extract in the same folder, or if you want to keep it under a specific say in C drive, you can also even do that. I will keep in the same downloads folder I am extracting. Now after extracting, you will find a new folder, SAGA 9.2.0, and if you open this folder, you will find another folder, because it is a zipped file. Inside zipped file you will find the same folder with the same a folder with the same name, and then if you double click, then you will find all these files, SAGA files. So these are inside this folder. So you need to give path to this folder, which is inside another folder with the same name. What you can do is, you can copy all these files, simply cut them and put in the outer folder. Yeah, and this empty folder you can remove. So I have under downloads the folder SAGA 9.2.0, which will contain all these files. So I have to get the path to this folder which has all these files. You can keep this folder in wherever you want on your system. You can keep it in C drive, or you can keep it in downloads. Make sure wherever you are saving this folder containing these files, the path should not contain any namespaces. For example, how to get the path? You can right click and then you will find this option of copy as path. And if you want to check the path, paste. So you see it is D, then your username, and then under downloads SAGA 9.2.0. So your username, make sure that your username don't is not having any spaces. So you can copy this path, or say if you want to keep in C drive, you can copy this. Right click. In case if your username has namespaces, you can directly keep it in C drive, and then you see the path copy as path. So the path will be simple C drive colon slash and the name of the folder which contains these files. Don't make mistake in this step. Now once you got the path, you need to give this path in the settings. So in the main menu, go to settings, go to options, and in the options general, in the left side panel, you go to processing, this option processing. So under processing, you can open this providers by clicking this GP. Then you will find these are the processing providers, which are additional processing providers other than whatever is the QGIS comes with its own algorithms. You have GDAL, GRASS, and SAGA next generation. So you can open this SAGA next generation and you check all the boxes. Check all the boxes, enable SAGA import export optimization, and all the boxes you make sure that you are checked. And in the SAGA folder, you have to give the path. How to give the path? You just double click here next to SAGA folder. You double click here and then you can paste your folder. You remove these inverted commas. So the folder should be simple, your drive name colon slash and then any folder containing SAGA folder. If it is contained in another folder, that path has to come here, and then finally SAGA dash 9.2.0 underscore x64. So this is the path, and then press enter. You can also browse the folder by clicking these three dots. Go to the location where you are saving. I have pasted it in the C drive 9.2.0 and select the folder. Again, in both cases you will get the same. You can copy as path and or you can browse it and then press enter. Make sure that it is the path is there and then click on OK. You can verify it if the path is there, because sometimes, yeah, it is there. Sometimes what happens is you type the path, and then you don't press enter, or you don't press OK. The folder path may not be, may be missing. You make sure that the folder path is given. Now I said that there is an alternative way of giving path. Like there is a folder which is already there in case if you have used the OSGeo for Windows network installer. We have suggested to make use of the network installer for installation of QGIS. So if you have followed the procedure, then you will find under C drive there will be a folder of OSGeo for W, OSGeo for W. You open this folder, and inside this you will have apps subfolder, and inside this you will have the SAGA folder. You can give path to this SAGA folder alternately after installation of SAGA next generation plugin. So again, right click, copy as path. You can check the path. It should be something like the C drive, OSGeo for W, apps, and SAGA. So you can paste this path in QGIS, settings, options, and then processing. Under providers, go for SAGA NG, that is SAGA next generation. Make sure that all the boxes are checked, and then in the SAGA folder you double click and paste your folder path. Both will work. You can download the SAGA binaries folder from SAGA GIS 9.2.0 and extract it and give the path to the folder containing the files. Or you can go to the OSGeo for W if you have used network installer folder, and then go to apps subfolder, and you find the SAGA and give the path in both way. So let me retain my original path. Yeah. Okay. In case here, if you are finding SAGA also, not SAGA next generation, but SAGA in older installations, you just make sure that all these boxes are unchecked. And also in the plugins, you can look for SAGA GIS provider. In the latest versions, you will not find it. It is deprecated. But still, if you find SAGA provider, SAGA GIS provider, then you can uncheck that plugin so that there will not be any compatibility or collision between the tools of SAGA and older tools of SAGA and SAGA Next Gen. Just make sure that processing SAGA Next Generation provider is checked, and make the settings, change the settings by giving the path to your SAGA folder. So that this is the setup that is required, that you need to do before proceeding to use the SAGA tools.
Now we will make use of SAGA tool fill sinks, the algorithm provided by Wang and Liu. Go to main menu of QGIS, click on toolbox, and you can search for fill sink. So you will have these multiple algorithms which are available. You can select this fill sinks Wang and Liu, double click it, it will open a
dialog box. You can see the documentation of this module fill sinks Wang and Liu. If you do a Google search, it will open the SAGA GIS module library documentation. Here you will find that this module uses an algorithm proposed by Wang and Liu to identify and fill surface depressions. It not just fills the depressions, but it also preserves the minimum slope gradient and thus the elevation difference between cells. So this one optional parameter, minimum slope, is very crucial. The value that you provide it makes a lot of difference. If you in case if you are using LIDAR data for large data sets, you can go for another algorithm which is available, like fill sinks XXL, that can be used. Whereas for this SRTM, we can go with this tool, and you can select the minimum slope. As you can see, minimum slope gradient to preserve from cell to cell. This optional parameter, the default parameter is 0.1. You can further decrease it. You can take it to 0.001. The least value that is possible is 0. If you select 0, then the sinks are filled up to the spill elevation, which results in flat areas. So let me go back. You in this you dialog box, you can select you have to select, because there is only one layer that is active in your layers panel, that is automatically selected. The DEM reprojected has to be your input elevation layer, input DEM, and then the minimum slope you can change it to 0.001, and then you can uh, save the filled DEM after filling of sinks to the file by giving it the location. You can save it as dem underscore filled. As you can see, it is being saved as .sdat file, which is another format of raster. You keep it as it is, and it will also generate flow directions raster after filling of sinks, and also watershed basins. Watershed basins, by automatically it will delineate some basins which may not be of much relevance to you, because the outlet point is being selected randomly. You don't require these things actually for the moment, but still you can keep them. They will be generated as a temporary layers, and then you can remove them. So you can now, after saving the filled dem onto your folder, save to onto your file disk, you run this algorithm. Kindly follow the steps as it is, because these tools have been facing some issue. So if you miss any of these steps, then you may not be able to generate these layers. Some error may come. So this algorithm is running. It may take some time. This is filling the sinks using the parameters that have been provided. In case you get a error like this, loading the W watershed layer has not been generated, then there is no issue. You don't require this layer. As long as you are getting your DEM field generated, then there will be no issue. Filling of sinks algorithm will take some time to run, because your area is a very big area comprising of BIMA and extended catchment areas. Once it is finished, the DEM field layer will be generated and will be added to your layer panel, and it will be also be displayed on the map canvas area. And also the temporary layers of watersheds watershed basins and flow directions has been created. Now if you check the flow directions, right click on the properties, you check the paletted render type as paletted or unique values and click on classify. Then it should display you uh, unique values from 0 to 7 as well as -1 where the water doesn't flow in any direction, flat areas, whereas 0 to 7 represents 8 cardinal directions. So I think flow direction has also come out to be good. Anyway, we will not work on flow direction at this point. And you can also check the watershed basins. A temporary layer has been generated. Here the basins, these basins are of not much use for us because we haven't defined our outlet points. They have been done uh, automatically. As you can see, I think this is the larger part of the larger Krishna basin. Your Bhima basin will come over this portion only. These are the west flowing rivers. Now I will remove these temporary layers. I will also remove the DEM reprojected. I will keep the DEM field uh, active, and this will be used for the next step of stream delineation. For stream delineation, you can check the processing toolbox and search for the tool channel network and drainage basins. Under SAGA next generation, you will find under terrain analysis, you will find this option of channel network and drainage basins. You double click it and a dialog box will open, and here you can give it is automatically it selects the DEM field because there is only one active layer here as the elevation, and then the threshold. This threshold is the threshold of stream order. By default it is 5. Let it be by remain at 5. If required we will change it afterwards. So it means all the stream orders of 0, 1, 2, 3 and 4 will not be displayed or will not be delineated when it delineates the streams. So it will not create a very high dense network which will not be of much use to us. And then it will also generate flow direction, sub basins flow direction. You can keep it, you can save the flow direction to file by giving the name. You can also flow connectivity, uh, then stroller order, drainage basins and channels is what is very important for you, because it is you have to define your pour point or outlet point on these stream network channels. So you can save it as channels.shp. This is a shapefile, and remaining things you don't require. Drainage basins, junctions, you can uncheck them. You can keep the channels, you can uncheck the drainage basins. Stroller order, you can keep it or you can uncheck if it is not required for now. Flow connectivity also, so you can keep the sub basins, flow direction and channels checked and remove everything else. You can save the flow direction and channels onto your disk, and now you can run this algorithm. Again it will take some time to run. In the previous step also, the flow directions raster has been generated. It will be again generated in this step also. We are more interested in generating the channels shapefile layer. We will change the symbology of the channels layer, and then we will match the channel network with the base map, and then we will identify the point of confluence of Bhima river with Krishna river, and then we will select the pour point or outlet point. So it will take some time to run this algorithm. Let it run. The channel network and drainage basins algorithm has taken around 7 minutes 23 seconds on my system for completion, and then the layers have been generated, the channels layer as well as flow direction layer. There is some error which is showing for Python error. You can neglect for the time being. And now you check the flow directions raster. You can change the visualization parameter by right clicking the flow directions raster, go to properties, check symbology. Now the render type is single band gray. You can change it to paletted or unique values. As you know, flow directions vary from 0 to 7 and then -1 for each pixel, and you click on classify. So here it is from 0 to 7, the and the level pixel is represented by the value 255. So you can apply it. You can check the flow direction grid. Then you uncheck everything else. So this is the channel network with the threshold of 5 that has been generated for your area of interest. Now you cannot make much out of this channel layer. You can change the display by going to properties, go to symbology. Now instead of single symbol, you can select graduated. Now this if you check the attribute table of this channel, it is a vector layer. The order of the stream or the channel is stored in this order field. Now you had given a threshold of 5 um, when for generation. Now if you see up to for order cell of 5, it has given an order 1. So the original stream order 1 2 3 4 have been not been generated. They have been excluded because of the threshold, and then the new order have been saved from the values ranging from 1 to 9. So original highest order stream is 13. Now it is 9. Now anyway, you can go to channels, right click on properties, go to symbology, and here instead of single symbol, you select the graduated and you display the graduated symbology using the order which varies from 1 to 9. You can change the color ramp, right click and then select blues. You can even change the starting color to light blue. For now it is very light, that is not visible, so you can change it and then press OK, and then you can click on classify. You can increase the number of classes because the orders are varying from 1 to 9. You can change the number of classes to 9 and then click on classify. Now then you can apply and then press OK. So this is the channel network. The greater the order of the stream, the thicker will be the tone of blue color is varying as per the order of the stream. So you can easily identify many of the major streams, which was not the case with the default visualization. So this is the major river. So these are all other. You can see. You can check the value of the stream order by clicking on identify features. This order is 9. The original before thresholding it was 13. So if any two streams of same order are merging, the resulting stream will have the next level stream order, which will be increased by 1. And if a stream order of 9 is merging with a stream order of with order 8, the resultant stream will be of order 9 only. However, if two equal order streams are merging, then the resultant stream will have the next higher order. This is how the Stoller order or the stream order is defined. So anyway, let us come back, zoom back. So in this way, you can change the channel symbology and you can identify your channels, main channels you can identify. You can even add the base map from your web option, quick map services, and then you check Google satellite as a base map, and also Google roads or OSM standard as a base map. Now you can check by changing the transparency levels. You can uncheck the Google satellite. You can see that your channel, you can verify your channel network that has been derived. Now wherever there is a water body, you will find that your channels are in straight lines, which is because the due to lack of information on elevation over water bodies. You can go to Bhima river. Let me uncheck channels. So this is the confluence point of Bhima and Krishna, and now you can activate your channels. So you can see this is your Bhima river, the thick one, and this is the Krishna, and the point of confluence is somewhere here. And if you want to generate the catchment area of Bhima river, you have to select your confluence point somewhere here before it merges with the Krishna river. You can verify whether your stream is following the
stream as per the OSM map. You can check even the Google satellite imagery. Now in the next step, we will try to identify the our outlet point, and then we will try to generate the catchment area. In order to get the actual coordinates of the pore point on your channel network, you can make use of a plugin, coordinate capture. You can install by clicking on plugins, manage and install plugins. You can search for coordinate capture. You will find this coordinate capture plugin, which captures the mouse coordinates in different CRS. While connected to the net, you can click on install plugin button, which will be installed, and then you will find the option of coordinate capture under vector main menu. You will find this option. In case you are unable to trace it after installation of the plugin, you can restart QGIS, or you can go to plugins and make sure that the checkbox next to coordinate capture is checked. So now launch the coordinate capture. It will open, it will be displayed as a panel. A new panel will be displayed in this manner. Now let us go to the confluence point of Krishna and Bhima. So this is Bhima is coming in this direction, and this is Krishna. The confluence is somewhere here. So you can look at the channels that have been generated. So this is Bhima, and it is merging with Krishna somewhere here. You can just select a point upstream of this and zoom to the maximum extent possible. And then you click on Start Capture button in the coordinate capture panel. You click on exactly on the channel to capture the coordinates of outlet or pore point. So these are the coordinates in longitude and latitude and in UTM 43 north projection. So you can capture these coordinates by clicking on this symbol. Then the coordinates are copied. Now we will make use of a new tool or algorithm, upslope area. You can search for upslope area. Under SAGA next generation, you will find upslope area algorithm listed under terrain analysis hydrology. You can double click it. Here you can in the dialog box you can copy your coordinates which are copied. You can paste your coordinates which are copied from here, and then remove the y coordinate. Similarly, you can copy the coordinates and remove the x coordinate. So you have pasted the x and y UTM coordinates, and then elevation you have to choose DEM field, the field DEM, and then the method default is multiple flow, but for the flow direction it uses deterministic 8. We have been using deterministic 8, and then you can skip saving to the disk, let it remain a temporary layer, the upslope area, and now run. Click on run. Now this algorithm will take some 5 to 10 minutes time for running and creating the upslope or catchment area. So let it run until it is finished. Once the upslope area algorithm runs and the layer of upslope area is generated, raster layer is generated, it will be added to the layers panel. You can close this dialog boxes, and you can go to the upslope area, which is a temporary layer. We haven't saved it to file. Uh, you can right click it and zoom to layer. So you can see that your Bhima basin has been generated in the raster format. Now what we will do is we will try to polygonize it. We will convert it into a vector, and then we will calculate the area of the catchment. So you can go to the option of raster and then conversion, polygonize, and then click on this. The input layer will be the upslope area, and don't change anything else. Then you can save it to file, the vectorized file. You can give it the name Bhima Catchment and save and run. It will not take much time, conversion from raster to vector. Once it is done, it is added to the layer is added to the map canvas as well as layers panel. You can change the symbology by right clicking and properties. You go to the simple fill and make it transparent fill by checking this option and checking this. And apply. You no longer require this upslope area temporary layer. You can remove it by right clicking and remove. And also the channels you can uncheck. So you can see that your Bhima basin has been generated. You can change the outline color as well as width. The stroke width you can increase and then apply. So this is your Bhima sub-basin. This is the outlet point where it confluences with Krishna. You can clip the channels up to the extent of the Bhima basin. Um, Let us first calculate the area of the basin. It also includes the Pune region. So you open this attribute table, and here you will find that there are 5 records. Now this upslope area algorithm, wherever the basin is, it will give you a DN value of 100, and outside the basin it will give you a DN value of 0. But there should be ideally only one record having a DN value of 100. In my case, I am finding some 5 entries. In your case, you may be finding different number of entries, even single entry, depending upon where you are choosing exactly the pour point. You may be choosing a just 1 point above and below that, then also it may change. So what you have to do is you have to check which of these records corresponds to your Bhima basin. So as you may remember, in the when we are dealing with the vector attributes, whenever you select any attribute, it will highlight the layer in the map canvas area. So if you check this first record is not being highlighted, second no, third one, fourth, fifth. So the fifth one is the actual Bhima catchment, whereas the remaining, because of some topology error, some error, there may be a small pixel which was considered to be the part of the basin, which may not be visible here, but you can remove it. We can remove all these 4 records and retain the fifth one. So to remove it, you can just
go to the toggle editing mode by clicking this pencil, and you can select each of these records, first four records, and click on delete selected features and then press S. So again you open the attribute table, you continue deleting, and then you can stop toggle editing either from here or from the attribute table and save your layer. Now you can check the attribute table. There is only one entry, and if you select it, it should select the catchment area on the main canvas. So now you can calculate the area by again going into editing mode. You can add a new field by this option of new field. You can name it as area of type decimal, and length and precision let it remain as it is. Now a new column or field of area has been generated. You deselect all the features. Now we will populate this column with the area by using its geometry. For that you can open the field calculator while in editing mode is on. You open the field calculator. Here you can check this option of update existing field instead of creating a new field. If you check this update existing field, you can check the area. So you want to update the area, an existing field. With what you want to update? You want to update with the area of that feature. Now area of that feature can be calculated by inbuilt function, which you will find under geometry. You will find this dollar symbol area. If you just select it, it explains, means the documentation will tell you that it returns the area of the current feature. So you can double click it into the expression box, and then you have already selected update the existing field area with this expression, and you can click OK. In case if you want, now the area will be in square meters because our units are in SI units. Everything is in meters. Now if I want the area in square kilometer, what you can do is you can divide it by 10 power 6 and then press OK. Now your area of the Bhima basin is about 70,294 square kilometers. Now you can come out of the toggle editing mode and save your changes to the Bhima basin. So you have added a new column, new field of area with the area of that basin. You can just do a random Google search for Bhima basin area. It is about 70,614 kilometers. So your area, your figure is more or less, it is okay. It is about 70,300. So this much variation will happen because of the DEM, inaccuracies in DEM, and wherever you are choosing the pour point, that also matters. So in this way you can delineate any catchment. Now you can make use of this setup. You can choose this project, you can save the project, and you can make use of this setup having the DEM field and channel network to delineate any catchment in this region using the same upslope area method. Now let us say I want to delineate the catchment of Khadakwasla Dam, which is in the same basin. So let me keep my channels on. You can see this is Khadakwasla Dam. This is the main channel. You have to take care not to select this another channel of lesser order. You can even select and check the order of the channel, which is of order 5, whereas this one will be of lower order 3. So you have to choose your pour point on this channel just near the dam so as to select the coordinates of your pour point. So let me zoom to the maximum possible extent, and then now you click on start capture. Click here, then your coordinates are captured. You can copy them. Again go to processing toolbox, upslope area under SAGA next generation terrain analysis hydrology. Where you can copy your x coordinate and y coordinates. Choose the elevation as DEM field and the method as deterministic 8, and then you run. Now this is a smaller catchment and it should relatively take less time than for the Bhima whole catchment. So it is running. Let us wait for 1 or 2 minutes. You can see the status of execution of the algorithm. Meanwhile, let me check the Khadakwasla reservoir catchment area. I think it is about 14,800 square kilometers. Meanwhile, it is still running. You can close other windows. It has almost taken the same amount of time. Now you can close the dialog box. You can zoom to the extent of the upslope area, the temporary layer, and you can see that this is the catchment of Kadakwasla reservoir, which is a subcatchment of the whole Bhima catchment. If you, as you can see, both the boundaries are coinciding here. You can polygonize this upslope area by going to raster conversion, polygonize raster to vector, keep all the options as it is, and then you can save it as Kadakwasla catchment and run it. Then once it is done, again you can go back. You can remove this upslope area raster temporary raster layer. You check its Kadakwasla catchment's attribute table. There is only one record, and if you select this record, you should be able to see in the map canvas area the catchment has been selected. Now let us calculate its area by going to the attribute table, go to the editing mode, add a new field. You can even add the units, kilometer square, decimal type, press OK, and then go to field calculator, update existing field, area kilometer square, and the geometry you select this function, and then you press divide it by 10 power 6. Yeah, and I think the realistic area is this one, 544 square kilometers. You can save your changes, and then you can look for Kadakwasla catchment area 540. It must be somewhere mentioned in the salient features of the dam somewhere. You can have a look, but it should be reasonably good. In the same way, you can making use of this layers channel. In this whole extent of this, there are so many dams in this region. You can calculate the catchment, you can delineate the catchment for any of the dam, any of the point, by selecting simply the pour point on the channel and then using the same upslope area method. You have set up this project. You can save it. You can use it for delineation of even a minor catchment. If you want to have a minor catchment, you have to go to the channel. So if I select my upslope area somewhere over here, the pour point somewhere over here for this small stream, it will create the catchment for this area. In this way, you can make use of this tool for calculation of any for delineation of any catchment. As per this document, which is available on the WRD Maharashtra portal, the Kadakwasla catchment area is about 502 square kilometers. So it is reasonably good. Our estimation, our as per the delineated catchment, the area of the catchment was 544 square kilometers. That's all for this session on hydroprocessing of dam and catchment delineation using SAGA tools. You can follow the same procedure for delineation of catchments using any other dam for any region. We have used SRTM 30-meter dam here. If you can also make use of Carto dam, which is available for download from Bowen portal. Carto dam will be very useful in case of northeastern India, where SRTM dam has lot many no data values. So you cannot make use of it for filling of sinks and then generating the streams and then delineate the catchment. You can make use of Copernicus dam, which is again an open access dam. All these dams are not very accurate, but they will give reasonable results, and they can be used for catchment or sub-basin delineation. But for if you see the streams that are generated, there will be not there are some many locations you will find them to be straight lines, especially if the elevation variation is low. Like if you go for Ganga Indo-Gangetic plain, you will find almost straight lines. The channels to be straight lines. This is because the input dam is not very accurate. It has some error. It has some limitations in vertical accuracy, but that is okay, good enough for catchment delineation. Your delineated catchment area will be different. It will be actually it differs from person to person depending upon the dam that is used and the pour point where exactly you are choosing your pour point or outlet point. You can compare the area with the authentic information, which may be on the basis of field survey, which you can take, you can accept it as the true value. Whereas this is for learning purpose, and you can, if it will be, if it is reasonable enough, then you can make use of the shape file generated for mapping of your catchment. You can add other map elements and other features in the map of your catchment area of your gauge station or your dam or any tributary of any river, and then you can use it for mapping purpose. And you can, once you make up the project, once you set up the project, like in this case we have done it for a larger area, and we can use the same stream network and DEM field for generating the catchment of even of any river. West flowing rivers are also there, even a minor catchment that you can generate. And if you remember, we have chosen the threshold of 5 to remove the smaller order streams. You can reduce the threshold and even generate a very dense network of streams and even generate the smaller catchments. By the procedure will be the same. Maybe the computational time may increase if you are reducing the threshold. So in the next session, we will be doing the same catchment delineation, hydroprocessing, and then catchment delineation using GRASS tools. Thank you.